Getting a rocket off the launch pad, yeah, it's incredibly hard. But leaving Earth? That's really just chapter 1. Welcome to The Explainer. Today, we're unpacking a massive logistical nightmare. Not just leaving Earth, but surviving a trip to Mars, and crucially, actually getting our astronauts back home safely. We're diving into 2 really fascinating sources today. First, a deep dive by aerospace engineer Gerald Block on rocket architectures, and second, a highly technical engineering study by Oxyon Energy that details exactly how we're going to manufacture rocket fuel on the surface of another planet. It's going to be a fun one.
All right, here's our roadmap for today. First, the deep space dilemma, then SLS versus Starship, the cost of Artemis, making fuel on Mars, the soft-say technology, and finally, our interplanetary future. Let's get right into it. Section 1, the deep space dilemma. Okay, so every deep space mission runs smack into a massive 2-part problem. First, the absolutely astronomical cost of launching payloads out of Earth's gravity well. And second, the impossible weight penalty of dragging all your return fuel with you all the way to Mars. It just doesn't work. You need a cheap way to leave Earth and a rock-solid way to fuel up once you actually get there. Now, to solve the Earth departure side of things, Gerald Black breaks down 2 different architectures for the Artemis program. Over on the left, you've got the current NASA plan. This uses the Expendable Space Launch System, or SLS, and the Orion spacecraft to get astronauts up to lunar orbit, where they rendezvous with a SpaceX Starship to head down to the surface. On the right, though, is SpaceX's original 2017 plan. That approach uses Starship exclusively to launch from Earth, refuel in orbit, fly direct to the surface, and return directly back to Earth. Section 2, SLS versus Starship. And this brings us right to the heart of a pretty intense aerospace debate. See, in his paper, Black makes a controversial proposal. He suggests completely phasing out the SLS and Orion programs after Artemis 3 and going all in on that simplified Starship-only approach. But a lot of folks in the aerospace community firmly defend NASA's current dual system plan, and our sources highlight some really critical counterpoints here. For one, NASA's plan integrates beautifully with the Lunar Gateway, which is their planned orbital outpost. Secondly, and this is a big one for safety, SLS and Orion have a proven launch abort system. It's got its own motor to pull the crew away in an emergency, which is something Starship just doesn't have right now. On top of that, there are serious concerns about Starship lacking crew certification and the fact that it hasn't yet pulled off an intact pinpoint soft landing in the water with a crew castle. So you can see why NASA is heavily invested in keeping SLS and Orion in the wicks. They are prioritizing those safety and architectural redundancies.
Section 3, the cost of Artemis.
Now, regardless of where you stand on the engineering side of things, the economic numbers driving this debate are, well, they're stark. Just look at this. According to a NASA Inspector General report, $5.2 billion. That is the estimated operational cost for just a single SLS and Orion launch for the first 4 Artemis missions. Breaking that down, it's $4.2 billion for the SLS rocket itself and another $1 billion for the Orion spacecraft, every single time.
When you stack that up against the projected costs of Starship, the difference is honestly staggering. Black ran the numbers and calculated that even when you factor in the dozen or so Starship launches you need for orbital refueling, utilizing NASA's dual transportation system increases the mission cost by a massive factor of 9.7 compared to just using Starship. Basically, almost 10 times more expensive. He argues that multiplying mission costs by a factor of 10 is just completely unsustainable if our long-term goals are building a permanent lunar base or getting humans to Mars. But you know what? That brings us to a massive pivot. Let's say Starship perfectly solves the economics of leaving Earth. Great. But that introduces a totally new problem. Starship runs on a mix of liquid oxygen and methane. To get a crew back from Mars, they need a fully fueled rocket waiting for them. So how exactly do we fuel it for that return trip?
Section 4, making fuel on Mars.
Okay, so since we absolutely cannot afford to lug the enormous weight of return propellant all the way from Earth, we literally have to manufacture that liquid oxygen and methane right there on the Martian surface. To pull this off, we rely on a super vital concept called ISRU. That stands for In-Situ Resource Utilization. Think of it basically as living off the land. The Martian atmosphere is packed with carbon dioxide, and we know there's water ice there. So if we can harvest that local CO2 and H2O, we can run chemical processes to generate the exact propellant we need for the journey home. This isn't just some neat sci-fi trick, guys. It is literally the only practical way to ensure our astronauts can actually make the return trip.
Section 5, the SOX technology.
To really understand how we achieve ISRU, we've got to zoom way in, from those giant rockets down into the highly technical weeds of the Oxyon energy study. Remember the MOXIE device, the one that actually produced oxygen on the Perseverance rover a couple of years back? Well, check out this incredible scale-up. The hardware you're looking at here is the Oxyon Wish and Scale Solid Oxide Electrolysis Stack, or SOXE stack for short. It's scaled up by a factor of 35 from that original MOXIE device. 35! It uses high chromium interconnects and a Scandia-stabilized zirconia electrolyte. I know, that's a mouthful. But basically, those materials perfectly match thermal expansion, which lets the system electrolyze the Martian atmosphere at a much, much larger scale. Now, generating oxygen is amazing, but remember, Starship needs methane too. Under NASA's Next Step 2 program, the team actually successfully integrated that SOXE device with a methanation reactor, which you can see right there on the left. Then they put this whole integrated setup into the Mars simulation test chamber at the Jet Propulsion Laboratory, that's the picture on the right, and ran a 100-hour test at relevant Martian conditions. The results? It successfully produced high-purity oxygen at 99.99% and achieved over 99% carbon monoxide conversion to methane. Absolutely wild. But here's the catch. The engineers have to make a deeply technical choice on exactly how to run this system. Option 1 is co-electrolysis. That's where you feed both carbon dioxide and water directly into the SOSE stack. The issue with that, if you push the voltage too high, solid carbon starts to form. It's a phenomenon called coking, and it will literally destroy the delicate cathode hardware. Option 2 is the alternative method, running the stack on pure water for steam electrolysis, and then using a separate reverse water gas shift reactor, or RWGS, to safely mix the output with CO2 later on. And when you look at the thermodynamic limits of these two methods, the data is incredibly revealing. Look at these numbers. Because direct co-electrolysis is limited by that dangerous coking threshold, it has to operate at a lower voltage. That means it only produces about 437 grams of oxygen and 110 grams of methane per hour. But if you use the alternative RWGS configuration to bypass those coking limits entirely, you nearly double your propellant production. You hit over 829 grams of oxygen and 208 grams of methane per hour. Sure, it requires more equipment mass to fly out there in the first place, but the efficiency gains once you're on the surface are massive.
Section 6, our interplanetary future.
All right, let's zoom back out for a second. What does all this incredible engineering and policy debate actually mean for humanity's timeline in space? Well, here's the chronological progression we're looking at right now. We have the Artemis 3 lunar mission, scheduled for mid-2027, followed by Artemis 4 somewhere in the 2028 or 2029 timeframe. But looking further out to Mars, the Oxyon study points out a pretty sobering reality. Even using their incredibly scaled-up technology, it is going to take 6 of these 65-cell SOXE stacks, running continuously for a 19-month window, just to produce 30 tons of oxygen. 19 months! And every bit of that has to happen completely automatically on the Martian surface before a crew can even launch from Earth. We have to be absolutely certain their ride home is fully fueled and waiting for them.
Ultimately, getting past these massive logistical and engineering bottlenecks requires intense focus and a whole lot of investment. As Gerald Black summarizes in his piece, he says, "We need to end expensive programs and substitute programs that will inspire the next generation, like building a lunar base and landing the first humans on Mars." Now, whether that means transitioning entirely to a Starship architecture or keeping the SLS as our backbone, the core goal remains the exact same: making deep space exploration a real, sustainable reality.
We've seen the sheer financial hurdles. We've explored the incredible ingenuity of in-situ resource utilization. And we know exactly what it takes to get there and to get back. But as we build the rockets and chemical reactors of tomorrow, the big question remains: are we really ready to fully commit to an interplanetary future?